Okay, thank you all for coming today. We'll get going with moving on through Chapter 7. Before I start that, if you still haven't taken your exam yet, especially, and you want to come see me for some last-minute questions, I'll just let you know what my availability is the next couple days, just so you're aware of it. So tomorrow, which is Tuesday, so both days, Tuesday and Wednesday, I'll have the regular office hours of noon to 1, but I should be around a lot more than that. So if you come tomorrow, between 10 a.m. and 1 p.m. I should be there, or about 3:30 p.m. to 6. So if you're not able to come during the regularly scheduled 12 noon to 1 p.m., you can feel free to stop by those times. And then on Wednesday, I should be available pretty much any time, 10 a.m. to 6 p.m. Just camped out in my office doing other things. So if you stop by during those times, I'll be there and happy to take any questions. So that's what we have for those of you that are still taking the exam, especially. If you've already taken the exam and want to talk about your results, we can certainly do that as well this week. All right, but we're today talking about Chapter 7 material, which is not going to be, of course, on the exam, but it's still important nonetheless. So what we closed with last time, we introduced the idea of the change in internal energy and being able to determine that by the sum of heat and work in a process. And then we introduced another parameter called delta H, enthalpy, which is very closely related to the change in internal energy, but is slightly simpler to determine because it only is determined by heat for a constant pressure process. So then what we have for delta H then is two possible signs. It can be positive or negative, and we want to understand then some of the differences between those two possibilities. So if we have an exothermic process, we classify these as exothermic or endothermic. And remember that delta H is determined by the heat measured at constant pressure, so that's what the relationship is there. And an exothermic process has a negative delta H. Delta H is less than 0. And so one way to think about this, this means that during the process, heat is flowing out of the system. So the enthalpy is less at the end than when you started with. So you can almost think of this as heat being released as a product of whatever process is happening. All right, so we know that if we burn almost anything, you release a lot of heat. So specifically, let's say hydrogen. Let's say we burn hydrogen in air, very explosive reaction. We know that it'll generate a lot of heat. So this would be an exothermic process, which means one way to think about it is we have the combustion process, which forms water, and then a second product of this reaction is heat. Now, heat obviously is not a chemical substance, but you can think of it as being also produced during an exothermic reaction. And then the other thing that happens during an exothermic reaction, remember that we have the system, which is whatever we're studying. In chemistry, the system is usually the reaction itself. And then you have the surroundings, which is everything else in the entire universe. And so when you have an exothermic process, the temperature of the surroundings increases because heat is being released to the surroundings. So I think it should make sense then that the surroundings warm up. All right, so an example of this, if you're a Yankee like me and you grew up north, you would have sometimes some very cold days where you'd use these hand warmers, and these hand warmers have they have iron filings in them and some sort of other I think chemical that speeds up the process. So when you open these up, they expose to air, and there's an exothermic reaction that releases heat. So anything that warms up like that would be an exothermic process when you can feel the heat being released into the surroundings. And then endothermic process is the opposite, obviously. So in this case, the heat would be positive, or delta H is positive. And that means heat is absorbed by the system. And you can also then show it as a reactant in whatever process you're describing. All right, so an example of this is there are some instant cold packs that don't require you, question? P is the heat measured at constant pressure. So Q is heat, and then when we put a little subscript P, it indicates that we're measuring it for a constant pressure process, which is specifically what you're doing when you're measuring delta H. And then, so for an endothermic process, an example of this would be these cold packs. the ones that you don't have to put in the freezer first, where you just crack open something on the inside of the bag and it gets cold. And one way that these can work is just dissolving ammonium nitrate. So if we take ammonium nitrate as a solid and then dissolve it in water, this is an endothermic process. So you have to put heat into the system to be able to dissolve this in water to make aqueous ammonium. So this is not really a chemical reaction, it's just a dissolution process, but this is an endothermic dissolution process where heat goes in as a can think of it as being as a reactant, and in this case the temperature of the surroundings decreases because the surroundings are supplying heat to the system, and so their temperature goes down. So those are just some conceptual, qualitative things we want you to know about endothermic and exothermic processes. And then another way we can depict this is with enthalpy diagrams. So especially for chemical reactions, we think about our system as being a series of reactants and products. And remember that whenever we have these parameters labeled with delta, what really matters is the initial and final states that we're in. Final minus initial giving you delta whatever, in this case delta H. So in a chemical reaction, the initial state is going to be the reactants that you're starting with. The final state is going to be the products that you end up with. And so if you have an exothermic reaction, which we're showing here on the left, exothermic means delta H is less than 0. If the delta H is negative, that means the enthalpy of the final state, which is the products, has to be smaller than the enthalpy of the initial state. So you can think of it like this: you have your reactants which have higher enthalpy than the products, and as you go from reactants and products, then you lose enthalpy, and your delta H is negative. And then in this situation, heat flows out of the system into the surroundings, and this is why we get an increase in the temperature of the surroundings when there's an exothermic reaction taking place. And then we can have the opposite process for an endothermic process. So in an endothermic process, the reactants are lower in enthalpy than the products. So as you go from reactants to products, the enthalpy is increasing. Delta H would then be positive. And then you have heat going into your system, which is then results in a temperature decrease with the surroundings. So a couple different ways of thinking about the same thing, but when we're talking about a chemical reaction specifically, the whole reaction is our system, and then when we talk about what's the final and the initial states of that system, the final state would be whatever the products are, the initial state is whatever the reactants are, and the delta H, the sign of delta H, is determined by the relative enthalpies, absolute enthalpies of those reactants and products. Alright, so that's kind of some more conceptual background about delta H. Now let's talk about how we actually measure heat and how we measure delta H in a laboratory setting. And again, this is something that will likely relate to some things that you do in the lab if you're taking the lab this semester. But let's talk about how we calculate heat and how we determine it experimentally. So let's think about this just sort of, brainstorm it a little bit or think about it intuitively. So one thing is that if we have more mass involved in a process, would we expect there to be more or less heat? I think it's fairly clear that that would be more heat, right? So the amount of heat is proportional to the mass of substance that you have, the amount of heat that flows into or out of that substance. And the amount of heat is also proportional to the change in temperature. So if we put more heat into something, we would expect the temperature to go higher than if we put less heat into that. So think about, boiling water. If you heat the water for a longer time, the temperature is going to be higher because you're putting more heat into it, and so the delta T, the change in temperature, is also proportional to Q. And so as we talked about in one of our earlier derivations, and we'll see it again in the next chapter, if we have heat being proportional to two things, heat is proportional to the mass of substance that we have, heat is also proportional to the change in temperature of that, whatever that process is. In that situation, then the heat would be proportional to the product of those two, mass times delta T. And then the common math trick that we play in chemistry is if we have a proportionality and we want to make it into an equal sign, we have to add a constant in there. So then the constant we call C, and that gives us this familiar equation: Q is equal to mc delta T. Okay? So that's what some people say, that Q is equal to m cap, but that's not an A, that's a delta. Let's be precise here. So Q is equal to mc delta T. So it's mass, a constant C, and then change in temperature delta T are the things that determine how much heat is involved in a process. So really when we go to a laboratory setting, we need to just measure the mass and the change in temperature, and if we know those two things and we know this constant C, we can calculate the amount of heat that was provided in that process. All right. So let's talk a little bit about specific heat capacity. That's this lowercase c here that we have in this equation. So just that's abbreviation C. It's the amount of heat that's required to raise the temperature of 1 gram of substance by 1 degree Celsius. Alright, so it's the amount of heat that you need to put into a substance to raise its temperature by 1 degree Celsius. Now, a point that sometimes causes confusion in this chapter, and I don't want it to, is that when we're talking about changes in temperature delta T, we can use Celsius or Kelvin, because the size of the degree in Celsius or Kelvin is exactly the same. So when we're talking about a difference in two temperatures, it doesn't matter whether we measure those in Celsius or Kelvin. When we subtract the two, the difference will be the same. So in this chapter, you can use Celsius or Kelvin, especially when you're talking about delta T's. They're interchangeable. Okay. Next chapter, that won't be the case. So let's not let that confuse us. But if it's a change in temperature, Celsius or Kelvin gives us the same difference. So it's the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius. One way, the reason it's called heat capacity is you can think of it as the amount of heat that's stored by 1 gram of substance. Although that's not really the most precise way to think about it, but it's an analogy you can use. The only specific heat capacity that I want you guys to sort of memorize, because you're going to use it a lot, we might not always give it to you, is water. So water has a specific heat capacity of 4.184 joules per gram Kelvin, or gram degree Celsius, same thing. Remember, Kelvin and Celsius are the same when we're talking about delta T. So it's this number here, 4.184, that we have for water, that you're going to use a lot in these types of problems, because as we'll see, in a lot of cases it's going to be water that's absorbing the heat for whatever process we're measuring. Okay, so that's how we calculate heat. It's a relatively simple equation with 3 terms. One of those is a constant, so the value of C depends on what substance you're adding heat or removing heat from. This is the value for water, but every other substance would have its own characteristic specific heat capacity that you'd have to use if you're measuring a heat process involving that substance. Alright, so that's the equation. The other slight variation on this is what's called molar heat capacity. So you saw that specific heat capacity is in terms of grams of substance, and that's actually the one that's more commonly used. But there is what's called the molar heat capacity, which is, as the name implies, is the amount of heat needed to raise the temperature of 1 mole of substance by 1 degree Celsius. So it's not used as commonly, but we do want you to be aware of its existence and how to convert between the two values. So molar heat capacity, as I said, is the amount of heat needed to raise the temperature of 1 mole of substance by 1 degree Celsius or 1 Kelvin. And then the abbreviation for this, because we don't really always like to confuse you with abbreviations, is just capital C. Or sometimes you'll see a little bit of a subscript M there to tell you that it's a molar heat capacity. But it's usually a capital letter, so specific heat capacity is lowercase, and just molar heat capacity is usually a capital letter with sometimes a little bit of an M next to it to tell you that it's molar and not specific heat capacity. The context will always tell you which value you're using, though. You know, whether we're talking about moles or grams of substance, and the units of the quantity, of course, are different. So if we want to find the molar heat capacity for water, we can use the specific heat capacity to get that. So if we have a specific heat capacity of water of 4.184 joules per gram Kelvin or gram degree Celsius, and we want to convert this into a molar heat capacity, all we have to do is convert this part of the units, grams, into moles. We know how to convert grams into moles by now, so that's going to be just the molar mass of water, which is 18. And that gives us then a molar heat capacity of 75.40 joules per mole Kelvin. So that's again the amount of heat required to raise 1 mole of substance by 1 Kelvin. So the two values are different, but if you have one of them, you can calculate the other just by using the molar mass relationship that we're also familiar with now. So those are two ways of reporting heat capacities of substances. For pure substances especially, we use either molar or specific heat capacity. Specific heat capacity, which in terms of mass is the one that will be used the vast majority of times. So this I just want you to be aware of, but we won't use it a whole lot. So then let's just work through a simple example problem of how we do this. So let's say we have an aqueous chemical reaction conducted in 50 milliliters of water, and the temperature goes from 22.31 degrees Celsius to 28.37 degrees Celsius. We want to determine the heat absorbed by the water. The temperature is increasing, so we know that heat is being absorbed, and we should then think of Q as being a positive quantity. Remember we talked about the sign conventions for Q last time. If heat is absorbed by a substance, then it's going to be a positive number. But that comes directly from the equation Q equals mc delta T, so we don't have to necessarily even remember that as long as we get the equation correct. So we need to use the mass of the substance, which in this case is water, the heat capacity for that substance, which is the one that I expect you to know, times delta T. So in this problem, most of the information is given to us, but not necessarily in a direct format. So the first thing we need is the mass of water, and something that we'll see a lot in this section is usually when you go into the lab and measure water, you measure it in terms of milliliters. You just use a graduated cylinder or a beaker and pour out however many milliliters you want. But the equation, of course, is in terms of mass. So here we have 50 milliliters of water, and we just have to remember that the density of water is 1. So the number of milliliters of water we have is equal to the number of grams we have. So the mass of water is not directly given to us here, but if we have the volume of water in milliliters, we have that number already. Then we just have to multiply by the density, which is 1. So we have 50 milliliters of water, and then a trivial conversion to go to grams of water is just that the density of water is 1 gram per milliliter, as we should all know. And so that means 50 milliliters has an equivalent mass of 50.0 grams. Okay, so that's the mass of water. Usually we'll give it to you as a volume, but you can just interchange the two for water because the density is 1. Doesn't work for every substance, but for water that's certainly true. So 50 grams of water is the mass. The heat capacity of water, as we said, is the one that you should know, 4.184 joules per gram. And then the unit for temperature can be whatever you want it to be, either Celsius or Kelvin. Not Fahrenheit, but any of those two, Celsius or Kelvin, is fine. Our temperatures here are in Celsius, so we'll just use Celsius. But as I said, they're interchangeable. And then what we need is delta T. And just like any quantity that starts with delta, it's just final minus initial. So our final temperature, the water raises from 22.31 to 28.37. So the final is 28.37 degrees Celsius. The initial temperature is 22.31, which means our delta T is 6.06 degrees Celsius. So that's change in temperature. And remember that delta T is the same in either degrees Celsius or Kelvin. Okay, so we could have said this delta T is 6.06 Kelvin. Anytime we're talking about a difference in two temperatures, the numbers will come out the same. So then we just have to go and put that number into here, 6.06 degrees Celsius, and then the product of mass times C times delta T gives us the amount of heat. The unit for C is in joules per gram degrees Celsius, so our unit for heat will always be in joules when we're using this equation. Alright, so that's the amount of heat that's absorbed by the water when it raises its temperature by that amount. Alright, now usually what you're going to end up doing, as we'll see, is that this kind of calculation, m times c times delta T for water, is going to be part of a larger problem. It's not always going to be something you just do by itself. We're going to find different ways of using this to then calculate different parameters for heat transfer or for chemical reactions, and that's what we're going to get into starting right about now. Alright, so any questions on that equation or how we use it? Alright, so one final example, just to show you a slight variation on the same theme, is let's say we know how much heat we put into the substance. So we have a 1 ounce gold coin, and a 1 ounce has an equivalent mass of 28.35 grams. And let's say that this 1 ounce coin absorbs 721 joules of heat, and we want to know how much does its temperature increase. So we gave you the heat capacity here, which is 0.129. Something that we'll see as we look at these values is that metals tend to have much smaller specific heat capacities than water, which means that their temperature will increase a lot more or a lot faster than it would for water, and you guys probably know that from your everyday life. Gold has a very low heat capacity of 0.129. In this case, though, we're looking for the delta T. So we're using the same equation, Q equals mc delta T. But this time we're looking for what is the change in temperature if we know what the heat is and we know the mass and the heat capacity as well. So we just solve for delta T. So heat is given to us in joules, so we just use that unit directly. The mass has to be in grams because our heat capacity is in grams, as it usually is. So we're going to use the 28.35 grams, which is the equivalent of 1 ounce. And then the heat capacity of gold, as we said, is different than water. It's a unique value for every substance, so it's going to be 0.129 joules per gram K. And then all the units cancel out except for our temperature unit, and when we work out the numbers, we get 197 Kelvin. Alright, so when you have a small heat capacity, if you put a little bit of heat into a substance, the temperature is going to raise by a lot, and we see that here. It goes up by 200 degrees. Water has a heat capacity that's about 40 times bigger than that. So there's differences depending on the substance, but just using the same equation to solve for a different parameter, in this case delta T. So if you, there's some variations on that, but really just one equation to worry about when we're talking about calculating heat. Now we're going to talk about any questions on that equation or that part of it before I move on. Alright, what we're going to discuss now is then how do we use this equation to help us learn some things about chemical substances or chemical reactions. And then, so the device that we're going to start talking about is what's called a calorimeter. And if you, in the chemistry lab, you'll likely see a calorimeter incorporated into at least one of your experiments. So what exactly is a calorimeter? It's a device that's used to measure heat, and it's pretty low tech, as we'll see. And now, what this does for us is that it contains the surroundings. Because as we said, whenever we have heat transferring into or out of a system, the heat goes from the system to the surroundings. And technically speaking, the surroundings is defined as the entire universe. So you might imagine that measuring something that's happening over the entire universe is quite difficult. So we use a calorimeter to contain those surroundings into a much smaller volume and allow us to measure it in a more controlled fashion. So what it does is that it insulates the system from the surroundings. So instead of the heat that's being lost from the system or going in the system coming from the entire universe, it just is contained in a very small volume. So it's an insulated container, and it's going to be filled with water. So it prevents the heat from dissipating all over the place and contains it so that you can measure it more accurately. And most often, the substance that absorbs the heat, or a lot of the heat that's involved in these processes, is going to be water. Okay. So the simplest calorimeter, I'll show you some diagrams of them as we go through the different types. There's a couple different types of them. The simplest one is just a coffee cup, and probably what you'll do in the chemistry lab would involve something low tech like that. So a styrofoam coffee cup is very well insulating, so any heat that's absorbed into the water inside of a coffee cup, to a good approximation, is going to stay contained in there, and you can then measure the temperature changes accurately, not have to worry about that heat going everywhere. And so that's what a calorimeter does. It just contains the surroundings into a much more manageable piece of the universe that we can easily measure. Now, when we're doing calorimetry problems, when we're making measurements with calorimeters or simulating those measurements in the types of problems that we would do in this course, there's three scenarios, there's three different possibilities for how this can work. So the calorimeter, as we said, is filled with water, and then it has some sort of container that also is including that water. So when we determine the heat that's absorbed or released by a calorimeter, there's three possible situations. So in some cases, this is not the most accurate way to do it. We're just going to assume that all of the heat that's involved in that process is absorbed by the water in the calorimeter, and we're going to ignore the substances that make up the calorimeter, the coffee cup or whatever other, more fancy container is used in the calorimeter. So the point is, if the problem states only the amount of water in the calorimeter and nothing about the heat capacity of the calorimeter itself, we just use that same equation. The heat for the calorimeter is just equal to MC delta T for the water. Alright, so sometimes to a good approximation we can assume that all of the heat for whatever process we're measuring is absorbed by the water in the calorimeter or supplied by the water in the calorimeter, and we just have to use MC delta T for however much water is in that calorimeter. Where again the heat capacity is the one that you should know, 4.184. And then in another limiting scenario, we will just give you the heat capacity of the calorimeter itself. Now this is not a specific heat capacity because the calorimeter is not a pure substance. The calorimeter is often going to have some sort of container that's made out of one material, a thermometer that's made out of another material, sometimes some separate insulating material. So you don't have a simple specific heat capacity, but you have what's called the total heat capacity of the calorimeter. And if that's the information that you have, the heat is just given by that value, which I'll abbreviate as capital C for the calorimeter, times delta T. So heat capacity is just in units of joules per degree. So if you know the heat capacity, you know the delta T, you can measure the heat that's absorbed by the calorimeter itself. And then sometimes the third scenario is a combination of these two. So if the problem tells you how much water is in the calorimeter and the problem tells you the heat capacity of the calorimeter itself minus the water, then the total heat for the calorimeter is going to be the sum of those two. So it's the heat capacity of the calorimeter times delta T. This is the heat that's absorbed by the calorimeter itself. And then the second term is going to be the heat that's absorbed by the water, which is the mass of water times its heat capacity times delta T. So this is the piece of the heat that's absorbed by the water. So a common source of confusion on these types of problems with calorimetry is, how do I know how to calculate Q? And it really depends on what information we give you in the problem. So sometimes we'll make the assumption that all of the heat is absorbed by the water or given up by the water, so you'll just use this scenario 1 here. Sometimes we'll group everything together, the heat capacity of the calorimeter, all the water and everything else that's in there. Sometimes we'll just group it together into one term, in which case you would use scenario 2, just heat capacity times delta T. Or sometimes we'll give you those two pieces of information separately. We'll tell you the heat capacity of the calorimeter itself, we'll tell you how much water is in the calorimeter, and then the heat is going to be then distributed amongst both of those. So there's 3 different ways you'll have to do it. It's 2 equations or possibly the combination of those 2. So you just have to look carefully at what information is in the problem to know what the correct way to do it is. And we'll see examples of all of these as we go through, so this will become more clear as we do examples. Okay? So that's what a calorimeter is. And the first kind we'll talk about is a constant pressure calorimeter. So this is that relatively simple coffee cup design. Sometimes you'll do a coffee cup inside of a coffee cup to make a better insulated system. But this is kind of what they look like. So you have a thermometer that goes through there, you have an insulating surroundings, you have water inside there wherever your reaction is taking place. So in a constant pressure calorimeter, the system is vented such that the pressure remains constant. And this is useful for processes that are occurring in the liquid or solid phases, especially in liquid phases, because for aqueous reactions especially, they occur in water, so the water that's in the calorimeter can also be the solvent for the reaction, and it makes it very convenient to, I probably spelled occurring wrong, because I always do, but anyway, it's useful for processes occurring in the liquid phase. So you'd have your chemical reaction happening, if you're doing a chemical reaction, inside of the calorimeter. You have water in there that absorbs the heat from that reaction, and a thermometer to measure the temperature change. So as I said, relatively low tech. You'd probably do something like this in your lab in a typical general chemistry course. Now, one application of calorimetry, as I said, we can study chemical reactions with it, and we'll learn how to do that here in a minute. But one application is to determine a specific heat for some substance, so an unknown specific heat value. So the way we do this, and this would just be a physical process, we're not actually doing a chemical reaction in this case, but we're going to take whatever solid we're measuring, we're going to heat it up. So this works when whatever solid we're measuring is insoluble in water. So if we wanted to measure the heat capacity, specific heat capacity of a piece of metal that doesn't dissolve in water, we would just heat it up first to some higher temperature than whatever the water is. We would chuck it into the water, I guess carefully place it into the water. So we place it into a calorimeter that contains colder water than whatever it is, because if there's going to be heat transferred between the object and the water, there needs to be a temperature difference between the two. So you place it into the calorimeter, which is filled with water, as we said. And then all we have to do is measure the initial and final temperatures. So the final temperature is going to be the same for both the substance that we place into the water and the water. Because whenever, as we said, whenever there's heat transfer between two substances, heat is transferred until the temperatures are equal. So once the two temperatures are equal, that's our final value, T final, and we'll have a final temperature value that we'll measure. And then we're going to also need to measure the initial temperature values for both the metal that we're measuring and the water. So they're going to have two different initial temperatures, but then when we combine them, there's going to be heat transfer until the temperatures are equal. So you have to measure the temperatures of both the starting and ending processes. And then what we have to realize is that the heat that flows out of the solid, so the solid's at higher temperature, so it's going to transfer heat to the water, is equal in magnitude but opposite in sign to the heat that's absorbed by the water. Okay? So this solid piece of metal that we're putting into the water is going to lose some heat because it's at a higher temperature initially, and the water is going to gain that heat, and the heat that is lost by the solid is equal to the amount of heat that's gained by the water. We just have to put a negative sign in front of one of them to account for the fact that the signs would be different. Alright, so the heat that flows out of and again, we can think of this as system and surroundings. If this piece of solid, this metal, is our system, heat flows out of the system into the surroundings, which is the water that we're placing it into, so that the two heats have to be equal in magnitude. And that gives us an equation where the negative of the mass of whatever solid we're placing in there times its heat capacity, which is our unknown, times its delta T is equal to the mass of water times its heat capacity times its delta T. And again, the two delta T's won't be equal because the two things are starting at different temperatures. The final temperature value will be the same, but the delta T for the solid should be negative because it's going to a lower temperature, and for the water it should be a positive number, but they won't be necessarily equal in magnitude either. And then what we're solving for is the unknown heat capacity. So we just solve for that C, which is going to be then minus mass of the water times heat capacity times delta T divided by the mass of the solid times its delta T. So the three things we need to know to be, or I guess the four things we need to know to be able to answer these problems, and if we're doing this in the laboratory, we would need to know the mass of the water that's in the calorimeter, the mass of the solid that we're heating up, and then we need to know the initial and final temperatures of both the solid and the water. And all that information together, we can solve then for the heat capacity of whatever solid is. And this is how unknown heat capacities would be measured in a laboratory setting. All right, so let's see how this works then with an example. So let's say we take a 10-gram piece of metal and heat it up to 75 degrees Celsius. So again, we need to know the initial temperature that we're heating that up to. We place it into a calorimeter that contains 50 grams of water and initially at 25 degrees Celsius. And then we see that the water changes temperature until it's 26.64 degrees Celsius. So remember, we're measuring the final temperature of the water, which I'm telling you here is 26.64, but that's going to be the final temperature for both objects, the water and the metal that we're putting into it. Because as soon as the temperature is stable, once we get to that stable 26.64 degrees Celsius, that's the place at which both of them have the same temperature and heat is no longer being transferred. Alright, so I'm only going to give you one final temperature value because the two things, the system and the surroundings, will have the same final temperature. Alright, we want to know what is the specific heat capacity of the solid. And so again, it's this equation here. So the negative of the heat that's lost from the solid is equal to the heat that's absorbed by the water. And then we could either just start plugging in numbers and solving at the end, or we can rearrange the equations if we want for an expression for the heat capacity of the solid. So again, this is the unknown that we're looking for, and so when we do a little bit of rearrangement, just a little bit of algebra, we get this expression that we derived in the last slide here for the heat capacity. And then we just have to plug in numbers. So this top term here, the mass of water, we're told is 50 grams. Heat capacity of water we're given here, but it's one you should know, as I said, 4.184. And then we need the delta T for both the water and solid. So delta T for the water, remember that we have to have two different values here. It's always going to be final minus initial. The final temperature of the water is whatever the final temperature of both things is, 26.64 degrees Celsius. And then the initial temperature for the water, as was said in the problem, is 25 degrees Celsius. So delta T for the water is 1.64 degrees Celsius, or 1.64 Kelvin, however you want to think about it. And then finally the delta, so that's going to go in here. The mass of the solid goes in the denominator. We have a 10-gram piece of that, so that's the mass of solid. And then delta T is going to be, for the solid, its initial temperature is 75. Its final temperature is the same one, 26.64. So again, the two things have the same final temperature, but the initial temperature for the solid, we heated that up to 75 degrees Celsius first. So that delta T is going to be negative 48.36. There should be a minus sign up front of there too that I accidentally dropped out. Alright, signs are a little bit of an annoying thing here, but if you're calculating a heat capacity, it should always be a solid number. You can't have a negative heat capacity. So if you get a negative number, it might just mean that you left out one of your minus signs, but it is important to make sure that you get the correct delta T values, which are likely to be different, and they have to be opposite in sign for the system and the surroundings. So once we plug those numbers in, what we should get is a heat capacity of 0.709 joules per gram Kelvin. Okay? So that's how we would measure an unknown heat capacity. We heat it up to a known temperature, we place it in water, and we measure the heat that's transferred between the two substances and back out the heat capacity from there. Okay, so any questions on that one? Okay, continuing on then, let's talk then how we determine delta H from a calorimeter. So now we're going to start talking about chemical reactions. So the last one we did was an example of a physical process where you're just measuring heat transferred between two substances that aren't reacting with each other and backing out a specific heat capacity from that. But the more widespread use of calorimetry in chemistry is to measure delta H or delta E for a chemical reaction. So recalling the definition of delta H, which we reviewed earlier, delta H is delta E plus P delta V, and as we derived last class, this is equal to the heat that's measured at constant pressure. So again, if we just use a calorimeter to directly measure Q, that gives us delta H for the reaction. So if we have a constant pressure calorimeter and we measure Q for the calorimeter, that is then related to Q for the reaction, which then gives us delta H. So it's we're going to use calorimetry then to also measure delta H. So the first step is to determine the heat that's absorbed or released by the calorimeter, and that comes from the same setup that we talked about for earlier. So the heat for the calorimeter is just equal to the heat capacity of the calorimeter times delta T. So again, this is the fraction that's absorbed by the calorimeter itself, plus the amount of water that's in the calorimeter times this heat capacity times delta T. So as we said, there's two possible terms there that we need to calculate Q for the calorimeter, and depending on the information in the problem, we use one of these two or both of these together, as I've shown here. The delta T for both these will always be the same because the calorimeter and the water are temperature equilibrated, but you have to know in some cases the individual heat capacities of the calorimeter as well as the amount of water that's in there. So both of those terms could go into calculating heat for the calorimeter. We kind of already learned how to do that. And then from there we relate that to the delta H for the reaction. So what we have to realize is that the heat for the reaction, remember that the calorimeter is our surroundings and then the reaction is our system. So if heat is flowing out of the system, it's flowing into the surroundings or vice versa. So that means the two are going to be equal in magnitude but opposite in sign. So once we measure Q for the calorimeter, the heat for the reaction, Q reaction, is just going to be the negative of that. However, the value that we get for Q reaction, this is not exactly equal to delta H because this value depends on the scale of the reaction. So imagine that we were measuring the amount of heat that was released when we burn gasoline, for example. If we burn 1 drop of gasoline, that's not going to be a lot of heat, but if we burn a gallon of gasoline, it's going to be a ton of heat. So this value that we measure, Q, for the reaction depends on how much substance we're using in that chemical reaction. So that doesn't directly give us delta H. Delta H is going to be usually per mole of substance or normalized to some balanced chemical equation that has that substance in it. And so what we'll then usually do is we'll say that the delta H for the reaction is equal to that heat that we measure divided by the moles of usually a product that forms in that reaction or one of the reactants, but some molar amount that's part of that chemical equation. So that allows us then to determine delta H for 1 mole of substance, and then that allows us to to compare one reaction to another. Because if we just measured Q here, that would be different depending on what scale we did the reaction on. If we want to actually know the inherent enthalpy change for that reaction in terms of 1 mole of substance, we have to take the Q that we measure and divide by however many moles of substance are involved in that chemical reaction. So there's going to be some slight variations in how we do this last step here, but the key point to remember is that this Q that we get from the calorimeter is for specifically how much substance we used in that reaction. If we want to determine it for 1 mole of substance or some other reference amount of substance, we often have to divide that amount by the amount of substance that we're actually using. Okay? So that's the concept. Any questions on that? So let's see then how this works. The first one we're going to talk about is just a heat of solution. So the enthalpy change when we dissolve a compound, which as we said can be positive or negative. So if we take 1 gram of ammonium chloride and we add it to a calorimeter with 50 milliliters of water, and the initial temperature is 22.3 Celsius, when we dissolve the substance, the final temperature is 20.98, so the temperature decreases by a small amount. And we want to know what is the enthalpy of dissolution for this compound in kilojoules per mole. And we're going to make some assumptions that the density is still 1 gram per milliliter and has the same specific heat capacity as water. All right, so even though we're dissolving a substance into water, we're still going to use the same value for heat capacity, which is a good approximation. We don't have to measure a separate heat capacity for that solution. So the process we're measuring here is taking solid ammonium chloride, adding it to water, and dissolving it to make aqueous ammonium chloride. And we just want to know what is the delta H for this process when this solid ionic compound dissolves and separates in water to its constituent ions, NH4 plus and Cl minus. And we're going to use the calorimetry data to help us do that. Okay? So as I said, the first thing we want to do in a calorimetry problem is measure or calculate the heat of the calorimeter itself. So as we said, the heat for the calorimeter is the mass of water, heat capacity of water times delta T, plus the heat capacity of the calorimeter times delta T. Now if we look at this problem here, did we tell you what the heat capacity of the calorimeter is itself? Do you see that anywhere? Alright, so yeah, don't doubt your ability to look, it's not there. So there's no heat capacity given in this problem, so we're assuming that all the water is absorbed, all the heat is absorbed by the water, so we're basically going to ignore that term there. So we don't have the heat capacity of the calorimeter itself, so we don't have to worry about that term. Okay? And so in this case, we just need the mass of water in the calorimeter, which is 50 milliliters or 50 grams in terms of its mass, because the density of water is 1. Heat capacity of water, which is 4.184. And then we need delta T. Delta T is just the final minus the initial temperatures for the calorimeter. So we have to make sure we do these in the right order. The final temperature is 20.98, which is smaller than the initial, so our delta T is going to be negative. And the exact value is negative 1.32. And so that means this heat term here is going to be minus 276 joules. Alright, so that means the calorimeter is releasing 276 joules of heat into the reaction, or into the substance, to be able to dissolve it. And then what we need is the heat for the reaction itself. And as we said, this is just equal to the negative heat for the calorimeter. Alright, so if the heat for the calorimeter is minus 276 joules, the heat for the reaction is just the negative of that, which is plus 276. Okay, so this is an endothermic process. The temperature of the surroundings are decreasing. We have to put heat into the reaction, so that's going to be a positive number. But remember, this is the amount of heat that is absorbed by the reaction for 1 gram of substance. Okay, so that 276 joules represents the amount of heat that is absorbed when 1 gram of ammonium chloride dissolves in water. What we want here is the enthalpy of dissolution in kilojoules per mole. So we need to divide this number by the moles of substance to get kilojoules per mole. All right, so if we have the mass, we can get the number of moles pretty easily. So delta H is then going to be the heat of the reaction divided by the moles of NH4Cl, and that'll give us then joules per mole. And so we just need to find out how many moles of substance we use. We use 1 gram, I'm running out of room here. So the moles of NH4Cl, we used 1 gram of that substance. And then we gave you the molar mass, and so we just divide by that to get number of moles. So the molar mass was given as 53.49. And so that means in this reaction we were using 0.0187 moles of ammonium chloride. And so we divide the heat of the reaction by 0.0187 moles, which is the amount of substance we used. This is in joules per mole. We want it in kilojoules per mole, so we have to multiply by 1 kilojoule over 1,000 joules, or divide by 1,000 to get the units right. And that gives us then a positive 14.8 kilojoules per mole. Alright, so this is an endothermic reaction, and this tells us that for 1 mole of substance, the amount of heat would be 14.8 kilojoules. 276 joules would be the amount for 1 gram. Okay? So that's how we use calorimetry to help us find enthalpies for chemical reactions. Calculating Q is the same as what we've been doing all day today, but then we have to relate that to how many moles of substance we have to be able to get it into a more usable molar amount, as we usually do in chemistry. Alright, questions on that one? Alright. Next one, let's just do one more here. So we have, I guess we'll do a couple more. So here we have an acid-base reaction. 50 milliliters of 1 molar HCl placed into a calorimeter, and we add 1.6 grams of solid NaOH, and the temperature raises by 7.27 degrees Celsius. We want to know what is the heat of reaction in kilojoules per mole of water formed. Again, we will typically specify the reference amount that we're using, kilojoules per mole of water in this case, and assume the solution density is 1 gram per milliliter and specific heat is still the same as water. Alright, so this time we're doing an actual chemical reaction. HCl plus NaOH, and we know that this is an acid-base reaction, which we learned in Chapter 6, which gives us water and NaCl. So this is a 1-to-1 reaction forming 1 mole of water and 1 mole of NaCl. So the first thing we should do is measure or calculate heat for the calorimeter, which again is given by the mass of water in the calorimeter, heat capacity, and delta T, plus the heat capacity of the calorimeter times delta T. Once again, in this problem, we don't have the heat capacity given for the calorimeter. We know how much water is in there. We're using 50 milliliters of solution, so we would approximate that as the amount of water we have. But we don't see anything about the heat capacity of the calorimeter itself, so we're going to once again ignore that term. And so the mass of water is, we have 50 milliliters, so that's going to again be 50 grams of water. Heat capacity is 4.184. And then delta T was 7.27. So this is Celsius, so I'll just keep this as Celsius. So we calculated heat of 1,521 joules. So that's how much heat is absorbed by the calorimeter when we mix together 50 milliliters of 1 molar HCl with 1.6 grams of NaOH. But what we need to do is we need to take delta H for the reaction, as we said, is going to be this heat divided by the moles of water that are formed. All right, that's what we're looking for, kilojoules per mole of water formed. Or in other words, the delta H for this reaction as written, 1 mole of HCl plus 1 mole of NaOH giving 1 mole of water and 1 mole of NaCl. So this is the delta H for this specific amount of substance we're using. What's the delta H going to be for the reaction on a 1 mole scale? So this is equal to negative of the heat for the calorimeter divided by moles of water, which is then minus 1521 joules divided by however much water is formed. So we have to figure out how many moles of water are formed in this chemical reaction. Alright, so we have two substances being mixed together, HCl and NaOH, and we have two amounts. We have to figure out which one of those is going to determine how much of the product is formed. So the moles of HCl that we use in this reaction, we had 50.0 milliliters of that solution, and the molarity is 1.00, so we have 1 mole of HCl per 1,000 milliliters. So this is now all Chapter 6 review. And so what we find is that we have 0.0500 moles of HCl. And then the moles of NaOH, we had 1.6 grams of NaOH as a solid. So we use this molar mass to find out how many moles of NaOH we added. And that comes out to 0.04. Alright, both of these have coefficients of 1, so the moles of each substance is going to tell us the amount of water that can form. NaOH is then our limiting reactant. So we have less moles of NaOH in a 1-to-1 reaction, so that means this is going to limit how much water is formed. They're 1-to-1, so the amount of water that forms is also 0.04 moles. So that's the number we're going to put into here, minus 1521 joules. The amount of water that actually forms in this reaction is 0.04 moles, because it was limited by the amount of NaOH we had. We didn't mix them together in a perfect 1-to-1 ratio. And then when we divide the two, that's going to give us joules per mole. We want it in kilojoules per mole, as the problem specifies, I believe. Yep, kilojoules per mole. So we have to multiply again by 1 over 1,000, 1 kilojoules per 1,000 joules, to give us the correct units. So this comes out to minus 38.0 kilojoules per mole. Alright, so if we have a situation, it's not going to come up a lot, but if we have a situation like this one where there's two reactants in the calorimeter, we have to use the limiting reactant to then determine the delta H in kilojoules per mole, because the limiting reactant is going to determine how many moles of substance are actually produced or involved in that reaction. Alright, so questions on that one? Alright, the last one we'll do for calorimetry is, we'll do it sort of in a stepwise fashion to just wrap this up. So let's say we take 50 milliliters of 0.1 molar barium nitrate, and we mix it with 40 milliliters of 0.1 molar sodium sulfate in a constant pressure calorimeter. The temperature of the calorimeter increases by 0.383 degrees Celsius. All right, so the first thing it asks us for is what is the heat for the calorimeter in joules. So we're mixing together two solutions. There's some sort of reaction happening that we haven't defined yet, and we're getting a temperature increase. Now, without any knowledge about the chemical reaction that's happening, we can calculate Q for the calorimeter using the equation that we've been using all day today. So it's going to be equal to the mass of the water in the calorimeter, heat capacity times delta T, plus the heat capacity of the calorimeter times delta T. And it looks like I again left out any information about the heat capacity of the calorimeter. That's not given here. We just know how much water is in there. We're using 50 milliliters of one solution, 40 milliliters of another. But we don't have anything about this. We ignore that again. But we have to be a little bit careful up here is when we're mixing together two solutions, the mass of the water is going to be the total mass that we're mixing together. So we have 50 milliliters from our first sample, which is 50 grams of water. We're mixing that with another solution that has a volume of 40 milliliters, which is 40 grams of water. And so that means the total amount of water in the calorimeter once the reaction takes place is going to be 90 grams. So we're mixing two solutions together here. So that was the only thing about this one that's a little bit different is when we mix two solutions together, all of the heat that's produced by the reaction can be absorbed by all of the water that's present from the mixture of the two solutions. So by mixing the two together, we have a total of 90 grams of water, and any heat that's produced in the reaction will be dissipated throughout that entire 90 grams of water, not just the 50 that we started with or the 40 that we added. The total is what's important. Okay? So we have 90 grams of water. Heat capacity of water. And then we're told that the delta T, it increases by 0.383 degrees Celsius, so delta T is a positive 0.383. Alright, so that's the delta T, 0.383 degrees Celsius, and so that means the heat then would be 144 joules, which is A. Alright, so that's the amount of heat that is absorbed by the calorimeter. It's a positive number because the temperature of the calorimeter is increasing. So that's the first step. The second step, determine the moles of precipitate that are formed. So as I said, when we're doing calorimetry, we measure a heat value, but that's specific to the scale of the reaction that we're doing. If we want to know it per mole of substance, we have to figure out how many moles of whatever substance that we're referencing to is going to be involved in the reaction. So the first thing we need for this is a balanced chemical equation. So we're taking barium nitrate as an aqueous solution, and we're mixing it with sodium sulfate, also an aqueous solution. So we should recognize from what we learned in Chapter 6 that these are two ionic compounds. So when we mix them together, we're going to get two ionic compounds as products, barium sulfate, where we take the cation from the first compound and mix it with the anion from the second. And then we make also sodium nitrate. Cation from this second ionic compound combined with the anion from the first. So barium sulfate, we should recognize from our solubility rules that this is insoluble. The heavier group 2 sulfates, calcium, barium, and strontium are going to be insoluble. So that one's our precipitate. This one remains dissolved in solution, and we need some coefficients here. We need a 2 there. And I think that's all we need. It's just a coefficient of 2 to balance this reaction. Okay? So that's the balanced chemical equation. We want to know how many moles of precipitate are formed. So this is totally a review from Chapter 6. We don't have to even think about calorimetry for this one. But we again have amounts for two reactions. We're using, two reactants. 50 milliliters of 0.1 molar barium nitrate. That's the wrong slide. And then 40 milliliters of 0.1 molar sodium sulfate. So we have amounts for both of our reactants. We need to find out then the limiting reactant. Alright, so the moles of our first reactant, barium nitrate, we have 50 milliliters of that solution. And then the molarity is 0.1. So you have 0.1 moles of barium nitrate per 1,000 milliliters of solution. So we have 0.00500 moles. And then the stoichiometric ratio is, again, this number, 0.005 divided by the coefficient, which is 1. So that's the same number. And then for the other reactant, which is sodium sulfate, we have 40 milliliters. Sorry, I didn't write that out correctly. We're looking for the moles of the second reactant, which is sodium sulfate. We have 40 milliliters of that solution. Also a molarity of 0.1. So 0.1 moles of sodium sulfate per 1,000 milliliters of solution. So we have 0.004 moles of sodium sulfate, and this stoichiometric ratio is that number divided by the coefficient, which is also 1, so still 0.0040. And this one has the smaller stoichiometric ratio, so this is our limiting reactant. So if we're looking for the moles of precipitate that form, which is what we're doing in this question, we start with the moles of limiting reactant. We've identified that the precipitate is barium sulfate, and so the moles of limiting reactant is 0.004, as we just determined. And then we use coefficients from the balanced equation to tell us how many moles of that product are formed. And we see there's a coefficient of 1 in front of barium sulfate. And there's also a coefficient of 1 in front of sodium sulfate. So it's a 1-to-1 mole ratio of our limiting reactant and the product we're interested in. And so we also then form 0.00400 moles of barium sulfate, which would be choice B. Okay? So again, a review of limiting reactants in this case, in solution chemistry, solution stoichiometry. This is how many moles of precipitate that form. And then finally, the last step is we're going to determine delta H in kilojoules per mole of that product. Remember that delta H is equal to the heat of reaction divided by the moles of product. In the first step, we said that the heat for the calorimeter is equal to plus 144, so then the heat of the reaction is going to be equal to the negative of that. So in the first step, we determined that the heat for the calorimeter was positive 144. Heat for the reaction is just the negative of that. And so same set of steps. We have minus 144 joules is the heat of the reaction. Moles of product we just determined on the previous one is 0.004. Now we want it in kilojoules per mole, so a common conversion we'll have to do in these problems is 1 kilojoule per 1,000 joules. So that comes out to minus 36. Kilojoules per mole, which is choice D. Alright, so those are the series of steps we're going to typically have to do if we want to find delta H for a chemical reaction using calorimetry. You find the heat for the calorimeter using those equations that we've learned today, and then you have to relate that somehow to moles of substance to get it normalized correctly to the amount of substance that you have. And it's important when doing these problems to sometimes think about the answers a little bit. So here we see that 2 of our answer choices are positive, 2 of them are negative. We know from the very first piece of information that we use, the temperature of the calorimeter increases. And remember, if the temperature of the surroundings increases, that has to be an exothermic reaction, which means delta H has to be negative. So these are also things that are important to, helpful to check on when you're doing problems like this. If you know that the delta T of the surroundings is going up, make sure that your delta H is negative, or vice versa. So always make sure that your answer is reasonable, and you can sometimes eliminate choices just by doing that little thought process. Alright, so that's how we use calorimetry for chemical reactions. The last example we'll do is with a constant volume calorimeter. And there's really nothing different about this. I just wanted to introduce some of the differences between this type of calorimeter and the types of reactions that we study with it. So another name for a constant volume calorimeter is a bomb calorimeter. And that's not because it's awesome, but it's because in most cases a lot of pressure builds up inside of this, because we're in a constant volume calorimeter, we're often studying reactions that involve gases, especially things like combustion reactions. When we burn something, we know that we're forming CO2 as a gas and water vapor, so we build up a lot of pressure. And so we do those in what's called a constant volume or a bomb calorimeter, which is a totally sealed container. So the difference here is that the container is totally sealed, so the pressure is not necessarily constant because we're not venting the system in this case. But the advantage of this is that it can be used with gases. Alright, so if we tried to do a reaction in a constant pressure calorimeter that involved gases, you know, the constant, as you said, the constant pressure calorimeter has to be vented to keep the pressure constant. And if we're forming a bunch of gases, those gases are going to escape from the calorimeter and a bunch of heat's going to escape with it, so it just wouldn't be as accurate. So this also, then technically speaking, a constant volume calorimeter measures delta E directly. Because when you're carrying out a process at constant volume, you have no work term, and that means delta E is just equal to Q. So this would give us delta E technically, although it's still, as I said, often used interchangeably with delta H. So we can still use constant volume calorimetry to measure delta H, because in most cases delta H and delta E are pretty much the same anyway in terms of their value. And the other advantage of a constant volume calorimeter is that the heat capacity of the calorimeter is usually known more precisely. And that's because it's a totally sealed system. We don't have to worry about gases or heat escaping through the vent that we have to use to keep the system at constant pressure. So this is a totally hermetically sealed system, no way for heat to get into or out of it. And so we can measure heat capacities and changes in temperature much more precisely. So really at a research level, if you really wanted to make accurate measurements of heat, you would use a constant volume calorimeter, just because it's a much better sealed system. You don't have to worry about heat or gases escaping through the vent, and you can just get things a lot more accurate. But in principle, it's very similar. It's an insulated container. We're measuring a chemical reaction, and we're using the temperature change of the calorimeter to relate that to the heat of the reaction. So really, other than some slight design differences and some slight advantages and disadvantages of each one, they're used for the same types of things, which is measuring heat. Alright, so as I said, this measures delta E directly, and the reason for that is that we said last time that delta E is equal to Q plus W. And we can rewrite work as being P delta V. Now, in a constant volume calorimeter, delta V is 0. So this whole term then becomes 0 in a constant volume calorimeter, which means delta E would be equal to the heat measured at constant volume. So when we measure heat in a constant volume calorimeter, we are technically measuring delta E and not delta H, but the two are used interchangeably, and usually the values are pretty much the same anyway. Alright, and then same thing here. The negative heat of the reaction is equal to the heat of the calorimeter, which is equal to the mass of water in the calorimeter, heat capacity of water, delta T plus heat capacity of the calorimeter times delta T. So the math and the calculations and all that are exactly identical to what we did for constant volume. There's no difference between those two in terms of how we set up the problems. There's just some slight differences, as I said, in the design of the devices and the ways that we use them. So especially for combustion reactions, this one's important and very useful for us. So the one example that we have for a constant volume calorimeter is going to be a combustion reaction. So let's say we take octane, which is one of the major components in gasoline, and we have a 3.45 gram sample of it, and we burn it in a constant volume calorimeter that has a heat capacity of 9.121. And then if the temperature of the calorimeter rises 17.7 degrees Celsius, what is the combustion enthalpy of octane in kilojoules per mole? So this is the typical type of problem you'll use a constant volume calorimeter for. You'll burn a substance inside of it, and then you'll measure the combustion enthalpy, the amount of heat that's released during the combustion, usually in kilojoules per mole or sometimes kilojoules per gram. The other way that these are used in real life is this is used to determine calorie contents in food. So if you look at the back of a food label and it says this has Calorie is another unit for heat. We usually use joules in chemistry, but calorie is another unit for heat. And you basically burn the food inside of a calorimeter to determine how much heat is released, and that tells you then the calorie content of that food. So that's another application of these constant volume calorimeters. But here we're measuring combustion enthalpy for a sample of octane. So like I said, we're going to first measure the heat, or calculate the heat for the calorimeter. And in this case we have, again, we could do it as mass of water, heat capacity of water, delta T, plus the heat capacity of the calorimeter times delta T. In this problem, are we told how much water is in the calorimeter? Any information about that? Anybody see it? Nope. So we don't know how much water is in the calorimeter. So basically what we've done here is we've just grouped everything together into this heat capacity here of 9.121 kilojoules. So the calorimeter likely has water in it, but this 9.121 kilojoules per Kelvin is basically the total heat capacity of all the water in the calorimeter, all the other materials that make up the calorimeter. So all we need for this problem is to use this term. A very common mistake that students make is when they're doing these calorimetry calculations with MC delta T, they try to use the mass of the substance as the mass that goes into this equation. Remember, this mass is the mass of water that's in the calorimeter that is going to determine how much heat is absorbed by that water. The mass of substance is going to be what's participating in the chemical reaction and doesn't directly absorb or release the heat itself. It's the whole reaction that does. So when you're using this term here, only if you know how much water is in the calorimeter are you going to use this MC delta T as part of your calculation. You're never going to put the mass of substance that you're burning into that part of the equation. So here all we need is the heat capacity of the calorimeter and delta T. So that heat capacity is 9.121 kilojoules per degree Celsius or degree Kelvin, or sorry, just Kelvin. And then the change in temperature is 17.7. So in this case, calculating the heat is relatively simple because we just have to do the product of those two, which comes out to 161.4 kilojoules. Okay? So that's the amount of heat that's absorbed by the calorimeter. And what that means is then the heat for the reaction, the amount of heat that's released when we burn this substance, is just the negative of that. But as we always have to keep in mind, this is the amount of heat, this is delta H, but only for when we use this specific amount of octane that we're burning. So if we burn 3.45 grams of octane, but what we're interested in is what is delta H per mole. So a lot of students stop here and they say, oh, delta H is minus 161.4 kilojoules, done. But that's the amount of heat, that would be delta H for 3.45 grams. What we're often interested in, or usually interested in, is going to be delta H per mole of substance that we're burning, or per mole of substance that we're reacting in another fashion. And so then the delta H of combustion is just going to be the heat of the reaction divided by the moles of octane. So the heat of reaction we determined is minus 161.4 kilojoules. And now we just need to put the moles of substance in the denominator. And once again, moles of substance comes from the mass. We use 3.45 grams of octane. And we just divide by its molar mass of 116, which is given to us, figure out how many moles that corresponds to. So this corresponds to 0.0297 moles. And so we put that number here. And divide the two, divide the heat of the reaction by the moles of substance, and that will give us kilojoules per mole. So when we burn 1 mole of octane, we're going to have a delta H of minus 5.42 times 10 to the third kilojoules. Alright, so there's always, and very often there's a lot of steps in these types of problems, but none of the individual steps, I think, are too different. So any questions on calorimetry before we move on to the last thing we'll talk about today? Alright, so the last thing we're going to try to go through, which is going to be important for stuff we talk about next time, is consecutive reactions. So it's not going to be exactly obvious why this relates to delta H and things just yet, but consecutive reactions is a situation where we have two reactions that are happening in sequence. One reaction happens and another one happens right after it. And reactants and products can be added together just like mathematical equations can. So let's say we have two generic chemical equations with just made up reactants and products that I'll just call A, B, C, and D. So let's say the first one is 3A plus 2D forms 4C. And then in a situation of a consecutive chemical reaction, what would happen is that one of your products, in this case the only product, is going to then react with something else to make another product. So this is what we call consecutive reactions, two reactions happening in sequence. And if we want to know what's the overall chemical equation, we can just add the two together. So whenever we have two chemical equations that are occurring in sequence, we just take all the reactants and we combine them on one side of the arrow, and we take all the products and we combine them on the other side of the arrow. So from the first equation, we have 3A plus 2B. From the second equation, our reactants are 4C plus D. So in the combined equation, all of the reactants just get combined together on the left side of the arrow. And then on the product side, we have 4C from the first reaction and 3E from the second reaction. So this would be then the combination of these two equations. But what we notice here is that we have, in this equation, we have 4C on the reactant side and we have 4C on the product side. So something that's formed as a product in one reaction and then used up as a reactant in the next is what's called an intermediate. Okay, so this is really the only new concept we have for these consecutive reactions is the idea of an intermediate, which is something that forms in one reaction and is consumed in a subsequent reaction. So in this example, C, the species C, which forms in the first reaction and is consumed in the second reaction, this is the intermediate in this example. And so whenever you have an intermediate, and especially when the equations are set up in such a way that the amount of intermediate that you form on one side, 4C, is equal to the amount that's formed on the other side, just like we saw for spectator ions, you can cancel that out. So if something appears on both sides of the arrow, you can cancel it out. It's not in net participating. And then the final equation, which is the combination of these two, will be written as 3A plus 2B plus D goes to 3E. So this would be the combined sequence of two chemical equations being written as one equation where the intermediate is now canceled out. So that's how we can add together chemical equations. Reactants on one side add up, and then products on the other side add. So let's just let's quickly go through how we do this. So if we want to combine two or more reactions, I'll just finish with this slide here and just put off the next one to the last one. This will be our last slide if you're getting antsy. So the steps for combining two or more reactions. First, we're going to write out the individual steps. So we do need to have individual reactions that are balanced before we can start adding them together. So make sure that they're already balanced before we start trying to combine them. So let's say in one reaction we generate HCl by using sulfuric acid and sodium chloride. So this is something you can actually do in the lab. If you take concentrated sulfuric acid, add it to sodium chloride, you can make gaseous hydrogen chloride, and then you form also sodium sulfate. Alright, so let's say this is one of our chemical equations. We have to balance it by putting a 2 here and a 2 there. So that's our first balanced chemical equation. And then let's say the HCl that we form in the first step we're going to use to dissolve iron. So we react iron metal with that HCl. I'll just write it out first before I balance it. So iron plus HCl to make iron 3 chloride and hydrogen. This is a redox equation, and if we use our rules for balancing, which I'm going to skip over quite quickly here because we don't have a lot of time, what we would get is a coefficient of 2 in front of iron, a coefficient of 6 in front of HCl, a coefficient of 2 in front of iron, and a coefficient of 3 in front of hydrogen. So we have to balance this one using redox approach, and that's what we would get. So we have two balanced equations that are happening in sequence. The HCl that forms in the first one is being used in the second one. The second thing we have to do is adjust coefficients to make sure the intermediates cancel. So what we're going to do then is we notice that HCl are intermediate. It's the only species that's formed in the first equation and then also used up in the second equation. But we see that there's only 2 HCl's formed as a product of this first one, and then there's going to be 6 HCl's used in the second. So we want those to be equal so that it cancels out. So what we're going to do is we're going to take this whole first equation here and multiply it by 3 to make sure that the coefficient in front of HCl is the same in both of them. So we triple that first equation there to get 3H2SO4 plus 6 NaCl going to 6 HCl plus 3 sodium sulfates, Na2SO4. And now the coefficients in front of HCl are the same for both equations, just on opposite sides. And then once that's taken care of, we can then add them together. So the reactants from both equations combine, so we get 3H2SO4 from this equation plus 6 NaCl. The reactants from the other one that we're adding to it, which is this one, are going to be 2Fe and 6 HCl. And then on the product side, from this equation, we have 6 HCl's and 3 Na2SO4 plus 2 FeCl3s, which are the products from this first equation that we're adding into it, and 3 H2s. And then we notice that we have intermediates, so HCl is again on both sides of the arrow. 6 HCl's cancels with the 6 HCl's there. So we remove it, and we finally write our final equation as 3H2SO4 plus 6 NaCl plus 2 irons goes to 3 Na2SO4 plus 2 FeCl3 plus 3 H2. You could have written the reactant products in different orders, but this is what you get on each side. So we make sure that the intermediates cancel, and then we can add them together. All right, thanks for bearing with me a little bit longer today, but I'll do the next one I'll do in class at the beginning if you want to try it on your own. And then we'll start talking about some other things, how we use this approach to help us with delta H calculations.